Whether you like it, well, I guess we'll have to see at the end of the day. So my job is to set the scene and explain what this is all about, and then probably, as part of this, might confuse you as much as I possibly can. And then the job of the rest of the speakers is to sort out the mess I've left with. So basically, this is pretty much for me like my normal teaching. When I make a complete mess and then Professor Vickers fixes it. So that's easy. So what I'm going to try to do is I'm going to try to talk about what the main ideas of Einstein's general theory of relativity are, and then talk a little bit about the consequences and how these ideas have been tested up to roughly today. But I have carefully removed quite a few things because they will be touched on by others. So I'm sort of going to tell you roughly what they are, but I'm not going to go into all the details. That will be a very long presentation, and so I'm not going to do that. Okay, so let's start from the beginning, kind of, and then go back a little bit from the beginning in the proper time travel fashion, like Professor Vickers will teach you how to do later. For the moment, it's only people with special training that are allowed to do this. And I'm completely certified, so for me it's okay. So, as you probably all know, because it was in the media, in November last year we celebrated 100 years of Einstein's theory of gravity. And basically it is a fascinating story from the beginning until today, because as you've probably also seen, just a couple of weeks ago we celebrated the first discovery of gravitational waves, which were predicted by Einstein already in 1916. So we've managed to beat the 100-year limit on that one, but just barely. And that's after nearly half a decade of trying. So we stick at it, and we see what happens. But, so 1915, the remarkable thing about this is that, contrary to common impression, Einstein's relativity is not some sort of immediate brain search and suddenly was all laid out in front of him like some sort of inspirational moment. It was more sweat and blood and tears and hard slog than inspiration. Of course, inspiration is there, and I'm going to talk mainly about that. And the remarkable thing is, if you look at what he did in the month of November of 1915, he published 4 very short research papers, 1 a week, and I would challenge any of my colleagues to hit that publication rate, and we wouldn't be able to. But the papers were very, very short. They were just little notes, essentially saying. And if you look at these papers now, you see that when he wrote the first one, on the 4th of November, his theory was not complete. When he wrote the second one, on the 11th of November, the theory was still not complete. In the third one, the 18th, you see this, I'm good, I can add 7s, so that you can trust me, I'm a mathematician. The third paper, the theory as we know it is beginning to emerge. And in the final one, on the 25th of November, he writes down what we call the Einstein field equations. So they are the one equation I'm going to drill you in how to understand. Is on the board, apart from this Greek letter lambda piece, which he didn't have at that time. And so basically, the theory was still developing. And the reason the theory was still developing was that he was being chased by a guy called David Hilbert. He was a much better mathematician than Einstein. And so once this guy Hilbert got the scent of how this could be done, they obviously communicated through postcards and things like that. Einstein felt, I need to speed up. I've been going at this for 10 years, but now someone else is doing it. I won't get away with this for much longer. So he raced, and at the end of the day, there's even been historical discussion as to who got there first. And now we know that Einstein actually did it first, but it was very close. Okay, so now, of course, today we think of Einstein's theory as an enormous success. It's important for all sorts of reasons. It's given us things I'll talk about: black holes, gravitational waves, time warps, all these fantastic things that make us excited and confused in some proportion. But this was not always so. In fact, as I'll also tell you, the first half century of this theory, it was basically a gradual descent into obscurity, where maybe as late as the 1960s, young researchers were still advised by senior scientists to stay well away from general relativity because it had nothing to do with reality. Now, luckily for those of us that are doing this today, those guys didn't listen. There were a few guys that said, this is too exciting, we need to do this. And so, it's a tale of 2 half-centuries. The first half-century where the interest in this basically declined. It was too complicated, with mumbo-jumbo mathematics. It had things like tensor calculus that no one understands, and probably still no one understands. There's people like me and James Vickers that teach it. So I can ask my students and they will tell you they have no idea what's going on. And then a second half of this century where things changed dramatically for a few reasons that I will come to. Okay, so this is roughly what we're trying to do. But I want to start in 1905 rather than 1915 because I think it's important to understand the difference between Einstein's general theory of relativity and his special theory of relativity, which he wrote down in 1905. So, the special theory of relativity is, in principle, a very simple thing. I believe you can teach it to almost kids my daughter's age, and she is going to be 11. Because it involves hardly any complicated mathematics. You need to be able to write down a square root, but you don't need to tell anyone that that's actually what you're doing. So, you can almost teach this in pictures. But the idea here is that you assume that the speed of light is constant according to everybody, as long as they move relative to one another with a constant speed. Okay? So if you've got 2 people running, one person standing here, let it be me because I'm lazy, I want to stand here and not move. And then we take Professor Vickers because he's a speedy runner. No, don't have to come. He's a speedy runner, and we ask him to run full pelt towards that wall. Okay, and then we ask each of us to measure the speed of light. We want to measure the same number. Okay? So this is a little bit peculiar. This is not how everyday reality works, right? You know that if you... So here's an experiment again. Don't do this. Okay? Imagine sitting on the top of a car driving down the motorway. And you throw a stone towards a car in front of you. Let's not do this, okay? But you know that what happens is the speed of the rock as you throw it is obviously bigger than that of the car because you're throwing it forward. So you add the velocities. But here with light, that's not how it works. You always get the same answer. Speed of light is what it is. End of story. And that has a few repercussions on other things. It implies, this is what you can work out in pictures, that if you have a moving object, it contracted in the direction of propagation. So it appears shorter than it is if you hold it down and measure it. So just take a measuring stick, run with it very fast, and if I try to measure it not moving, I will see it as slightly shorter. Okay? A clock that moves will appear to run slower. So this leads to things like the famous twin paradox, where you send your twin off to the stars near the speed of light, and then let them come back, and then you try to figure out who should actually be the oldest or youngest, and so on. So it's a famous thing. And finally, we have in special relativity the most famous of all equations, which I refuse to write down, which is that E equals mc squared. So energy and mass are equivalent, with all the different implications that this has for weaponry and other unpleasant reasons. So this was a special theory of relativity. Now this theory was an immediate success. There was never any doubt that this was correct, there was hardly any discussion, etc. It was an immediate success because the scientific world was primed for this to happen. Quite a few people are working on similar kind of ideas, and typically we think that if Einstein hadn't done this, someone else would have done it pretty soon, around that sort of time. So what it does, it reconciles Maxwell's theory for electromagnetism and light with how objects move. But this theory is incomplete, and Einstein knew that this was not the final answer. In fact, he knew that there was a massive problem with this. The problem is, if you have a fixed speed of light, the theory says that nothing can actually a material body can never reach the speed of light. So the speed of light sets a limit. It's like going down the motorway when you know you shouldn't be going faster than whatever the speed limit is. But you refuse to do that, of course, because you know that psychologically you always get there much, much faster if you go faster than the speed limit by 2 miles an hour or something like that. Right? In special relativity, you cannot. You cannot beat this speed limit. But this contradicts Newton's age-old theory of gravity. You know, the famous inverse square law that says that gravity is a force that the strength of which falls off as the inverse square of the distance. Okay? But this theory says that if you change gravity over here, say by having 2 stars going around one another like this, the gravity changes all the time because the position of these guys change, then a guy over there, maybe Albert, on the poster, will feel this change immediately. Because that's what the mathematics tell us, that this happens instantaneously over there. But that can't happen, because special relativity says it has to take this signal, this information, a certain time to get over there. So there's something wrong here. Either special relativity is wrong or incomplete, or gravity has to change. So the obvious thing is, if you're a scientist, you want to take on the authorities, so Einstein now has to bring down Newton. So here we have the Germans against the Brits. And so, okay, so what happens next is it's a classic story, which I think is best illustrated by a cartoon. This is done by well, the husband of one of our PhD students, Ollie Dean, who is extremely talented as an illustrator. And so, what happens next is set in 1907, and it's based around 2 thought experiments. The first one, which actually Einstein describes from 1907, is basically he's sitting there in the patent office. Note, he published special relativity, was immediately accepted, but he remained the patent clerk in Bern. He got a promotion to technical assistant level 1. I don't think that had anything to do with special relativity. I think that was more about rejecting crank patterns. But that's maybe. So, 1907, he's still working in the patent office. If you know all these cartoons, he's got the desk drawer open. That's where he snuck his calculations in. So when the boss isn't looking, he's calculating. A bit like me. And then he had this idea, seeing a couple of window cleaners at work at one of the neighboring buildings, he had this idea that if what he described as is the best thought in his whole life. Now, keep that in mind, because this could become a bit nasty. He has this idea that the window cleaner falls off the ledge and starts plummeting towards certain death. So that's Einstein's best thought. Scary, I think, okay. But the best thought is actually not that man would be falling. The best thought is that as the man is falling, he would not be feeling gravity. Okay, now you're thinking, he would surely feel gravity when he thumps against the ground. It's going to teach him a lesson. But as he is falling, he will not sense gravity. So the way I think about it is, take a bathroom scale. Again, don't do this experiment at home. It's not safe. You have to be, actually now you have to be certified to carry this out. Take the bathroom scales, jump out the window from a high building, and ask yourself, what is the readout going to say on this bathroom scale as you plummet towards your certain death? The answer is, it's going to say you weigh nothing, because the bathroom scale accelerates towards the ground at the same rate as you. Okay? So, then the leap of imagination that Einstein took was to say, okay, but what if I change this situation so that I put rocket boosters or something on my desk chair and I shoot upwards at high speed or accelerate upwards as the guy is hovering in outer space where there is no gravity? How do I tell the difference between these 2 situations, the falling man and the accelerating chair? And he figured, I can't. There's no way I can tell the difference between these 2. And so therefore, I can't tell the difference between gravity and acceleration. they have to be the same. If I can't tell the difference, they have to be the same. So he called that the equivalence principle. And that's basically the foundation of general relativity. Okay? So I'm going to add to this now another thought experiment, which builds on things that Einstein was thinking about more with special relativity. With special relativity, I kept thinking about what would happen if I managed to catch a beam of light or ride along with it, which I just told you you can't do. So that was basically his solution, which of course, if you ask our undergraduate students to explain something and the answer is you can't, they get kind of upset and we get upset and all sorts of things. But Einstein's answer to trying to ride along with a beam of light is you simply can't. But now, take this accelerating situation, and so he put himself in a lift in the next thought experiment, and he assumed, let the lift accelerate upwards to high velocities, near the speed of light, and then imagine a beam of light entering the lift from one side. I'll go from that side, so that side. Now, the light moves at a constant speed. Light is lazy, it wants the shortest path between 2 points. But the lift is accelerating upwards. So this constant speed light beam comes in, and as the lift accelerates upwards, it will seem to curve towards the floor of the lift. Okay? This is very, very important. Okay? So this says, in an accelerating lift, light beams will seem to curve. But we've learned from up here that acceleration and gravity are the same. And so therefore, light beams will curve because of gravity. Curve because of acceleration, they will also curve because of gravity. So there we have it. What does this tell us? Well, it tells us that gravity should bend light. So how do we achieve this mathematically? That became the challenge that Einstein struggled with from 1907, when he had these ideas, the equivalence principle, to 1915 when he wrote down the theory. And basically, when he started this journey, he didn't have the mathematics he needed. He needed to rely on friends and colleagues like famously Marcel Grossmann, whose father actually got Einstein the job in the patent office in the first place. So we've got him to thank for quite a lot. To teach him things like tensor calculus and the mathematical machinery that we use. But, so in order to understand, not the mathematics, because we don't need that now, but how this works, imagine what light does. So light is lazy, like me and most university lecturers. We teach 3 hours a week or something like that. We get a full salary out of that. It's amazing, really. Don't do anything else. You know, you probably have breaks all summer and all sorts of things, like proper teachers. But light is lazy. Light likes to take the shortest path between 2 points. Okay? So now the question is, if the shortest path between 2 points is a curve, what does that tell you? Well, it tells you that the surface you're moving on is not a flat sheet of paper. So the flat sheet of paper, the shortest path is always a straight line. But if you're sitting on the surface of a ball, then the shortest path between 2 points is a great circle. And so that is not flat in that sense. If you take two neighboring great circles, they will meet. Start off at the equator, they will meet at the North Pole or South Pole. So they're not straight and parallel as two straight parallel lines on a sheet of paper. Okay, so that's the idea of why we can achieve the bending of light by messing about with the geometry and the shape of space. Okay, so that takes us to Einstein's equations again. Here, I've copied that again. And so the idea now is that gravity is due to the geometry of space and time. Special relativity tells you you have to combine space and time into one thing that has 4 dimensions. And general relativity tells you that this thing, combination, has a non-trivial geometry. And then, by messing with this geometry, you can essentially achieve the moon going around the Earth by simply saying that the Earth curved space and time. So this is a picture that we're reproducing on an experiment out in a cafe later, but it's a little bit misleading, but it's the sort of typical mental picture of how this works. Where it's the curvature that forces this guy to go around in a circle, and basically what you can think is that the moon is always falling in this curved space, and it's just falling, it's trying to move in a straight line, but it's falling just a little bit because of the curvature towards the Earth all the time. So that's how it goes. Or in the mathematical sense, you'll be tested on this later, okay? The Einstein tensor, which could have something like 100,000 terms in the mathematical expression, leave this out for now, balances the stress energy tensor for matter. So mathematically, there's some numbers like Newton's gravitational constant, pi, which would be nice because I didn't have enough breakfast, and the speed of light to the fourth power, and then 8, because we understand 8. So this says, you take all the matter in the universe, put on the right, you know where it is and how it moves, and then that tells you what the shape of space should be on the left. Simple problem. Einstein said famously, when he wrote down the theory, these equations are so complicated no one will ever solve them. Aha! Just a couple of months later, or a couple of weeks later, Karl Schwarzschild found a solution to these equations. The solution we now think represents black holes, and then he died in the trenches. But maybe that was his punishment for being too clever. So we know solutions to these equations, but that's not so important now. All you need to know, to understand what's going on, is that we've got a bit of geometry on the left, the shape of space, if you want, and we've got stuff on the right. Okay? And then, in the words of John Wheeler, matter on the right tells the space on the left how it should curve and bend, and then the curvature of space on the left tells the matter on the right how it should move. So this is a balance. It's just, a tug of war between the shape of space and where the stuff is. Now, if you want to do this in reality, which is what we're trying to do in our professional capacity, I guess, we need to know what to put in here, and we need to limit ourselves to things we can deal with. And then we need to know how to solve some complicated questions. But that's not so important for understanding roughly what's going on. So I'm not going to go into this. So let's summarize where we are. In 1907, the equivalence principle, acceleration and gravity are the same. 1915, so that's a good thing to point out to our students when we do this, that don't expect things to come for free. This is 8 years. Okay? The mathematics is complete, we have the equations. So now what about the implications? Well, what does Einstein's gravity do? Well, Einstein's gravity moves mass. That's what gravity does. Like stuff falls. Everything falls down, nothing ever falls up. It's disappointing, but that's the way it is. So, Einstein's gravity obviously does that. If it didn't do that, it wouldn't be much of a gravity theory. But Einstein's gravity bends light. We've seen that. I talked you through how that works. It warps time. So, in addition to having moving clocks slowing down, now we have clocks that sit closer to the ground running slower than clocks at high altitude. So, I bet you've never thought of this, but your heads are actually a different age from your feet. Unless you spend all your time lying down, which as a lecturer maybe I Gravity makes waves. We have gravitational waves because this space-time is not a rigid fixed thing, it's flexible. And so Ian Jones is going to show up at some point in the day and give you a dazzling presentation about that, which is always very exciting because we've now seen these. Gravity makes black holes. I'm going to tell you a little bit about that, and then Marco Calderelli will tell you some beautiful things about the interface between black holes and quantum physics later. So if I don't confuse you, I'm sure he will. And finally, gravity attempts to explain everything. Not everything in terms of the fine details, but the whole of the universe, the cosmos. So I want to talk a little bit about that. So the big question now is, here we are, 1950, how do we know that this is correct? So 100 years ago, how did people know that this was correct? Well, Einstein, of course, was supremely confident. I mean, you have to remember, he worked on this for pretty much 10 years, so if he didn't believe in it, who would? So he had good reasons. First of all, what he had done was he had used the theory. In one of these papers from 1915, he had worked out what's called the perihelion shift for the planet Mercury. And that's basically how much the orbit of Mercury, as it goes around, marches forward. So there's a tiny, tiny correction to the effects of all the planets in the solar system that was unexplained for about half a century. And Einstein worked this out, and he found that his new theory explained that tiny, tiny little missing bit. It was not a major part, it was just a tiny little correction, something like a 100th of the effect of the planet Jupiter. So it's not the leading term, it's just a small correction. And then the theory obviously predicted light bending. And I think here's another sobering context kind of story, because the light bending, as I've described it to you, is entirely due to the equivalence principle. It has nothing to do with those fancy equations. It's just this idea that light should bend under gravity. So Einstein had this in his theory already before it was finished. He wrote down the first light bending results in 1911. And then he tried to convince astronomers that it would be a really cool thing to go and detect this. And they told him he was crazy. But he insisted, and finally people realized that you might be able to see this during a solar eclipse. Because what would happen would be that the light from the stars would be curved a little bit, so it would be displaced away from where they would be if the sun was somewhere else in the sky. And of course, you know you shouldn't go out and stare, well, of course, today you probably go out and stare at the sun as much as you like. You might have trouble finding it, but in a normal, when the sun is out, you shouldn't stare straight at it. But during a solar eclipse, you can imagine looking at the limb of the sun and seeing stars slightly displaced. So Einstein wrote to a number of astronomers. Here's a copy of a letter from 1913, where he describes how this would be, how big the effect would appear. And the astronomers actually listened, for once. So some people set out to do this measurement. Famously, one particular expedition to the Crimea, a German expedition to the Crimea, set out to do this measurement. They got all the way to the site, waited for the solar eclipse. War broke out, and the leaders were arrested and shipped back to Germany. Now, Einstein was very lucky at this point, because the theory he'd given to the astronomers was wrong. They would not have confirmed his theory at that point. They would have told him he was wrong by a factor of 2. The factors of 2 are not that big in astronomy, but the error bars on the eventual measurement from 1919, Eddington's famous expedition and his speech to the Royal Society, etc., that confirmed the new theory from 1915, straight after the end of the war, was still only accurate at sort of 30% level. So, you know, it's not a big shift here, but would Eddington have returned to the Royal Society bombastically claiming that, you know, lights askew in the heavens, blah, 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 we have a new theory of gravity, if he tried to prove the original theory, but the error bars would have been huge? Maybe not. What would have happened to Einstein's effort at that point? You know, if you, the physicist, mathematician, sometimes you're a bit sensitive as to what's going on, and you might be incredibly hurt by something going against you like that. So maybe, even though war is a disaster in every sense, Einstein was kind of lucky that the First World War happened, so he could complete the theory. Secondly, he was perhaps lucky that Eddington, as a Quaker, was a peace-loving man and saw something aesthetically pleasing in the idea that he could prove a German scientist write, straight after the war, when sentiments were sort of swaying in other directions. So there are all sorts of historical aspects here that I think are very interesting, which I obviously want to talk about. But I think it's important to keep in mind. So now, zoom forward to 1955. Albert Einstein has been working at the Institute for Advanced Study in Princeton for 20 years or so after escaping the Nazis. Nothing much has happened to his theory of gravity, other than he's tried to build on it since 1915, did some other things, but mainly this was his effort, and got nowhere. So he left his desk. This is a picture, a famous picture from his desk the day after the day that he died. He basically left us with a bunch of unfinished calculations that were going nowhere and a lot of unanswered questions. Like, how does this work? Is it real? And so on. So what happened next is where this story changes gear to what we're talking about today. And it happens for three reasons. First of all, measuring technology had improved dramatically. At the end of the 1950s, we had atomic clocks that could measure time with extreme precision. If you want to check these things about space and time, you need to measure time very accurately. So that was the thing. Radar technology from the Second World War, basically, instead of searching for enemy planes, the radio telescopes were turned to the skies, and that led to a revolution in astronomy. Took astronomy to where we are today. And finally, a group of young researchers went back to Einstein's mathematics and tried to understand some questions as to what happens, in particular, what happens when gravity becomes too strong for matter to hold itself up. What we now think of as gravitational collapse leading to the formation of black holes. So, the formation of black holes had been discussed already in the late 1930s by Robert Oppenheimer and his students. But Einstein didn't really believe in those sort of things. He thought something had to stop this from actually happening. And so this was a big change as well. So I'm going to zoom through a few things on where we think we stand today. And it may be appropriate to start with the light bending, because I talked about how the light bending was an important confirmation of the theory. So, where are we with light bending today? Well, today, instead of measuring at the 30% level, we have long baseline interferometry. That's basically when you've got radio telescopes that are very far apart, that measure the same kind of signal, that allow us to check the light bending whenever the sun is out or not, because they're using radio waves, from distant galaxies, so active galaxies called quasars, and this tests the theory to 1 part in 10,000, which is good enough that you say, well, that is probably true. Light does bend under gravity. So let's keep that. What's going to happen next is that ESA's Gaia mission, so the Gaia mission is essentially an attempt to map the location and movement of a large fraction of the stars in our galaxy. So what comes with that is implicitly a measurement of the light. And that will eventually, in a couple of years' time, probably bring down the error bars on the light bending to about 1 part in a million. At that point, you get to the point where it's difficult to explain what's going on with other theories. You know, it's very, very fashionable, has been ever since 1915, I guess, to try to topple Einstein. I don't know why this is some sociological aspect, perhaps, which I'm not an expert on, which is you always have to topple the giants. And so there's a lot of effort going into trying to prove that Einstein was wrong or do better than Einstein, because I don't know what that proves, and so on. But it will be very, very difficult for these efforts once you squeeze the error bars on the theory down to 1 part in a million. Because then you get to the point where people say, well, who cares? If it's that accurate, do I really need to do better than that? But on the other hand, I remember my PhD supervisor, sadly departed, telling me that if you have this number to 6 decimal points, a number that no one would ever care about, Why don't you calculate it to 6 more decimal points? At that point, I think I could have strangled the number. But I calculated it to another 6 decimal points that no one will ever care about. So funny enough, that number that I calculated, though, is one of the numbers that was almost detected by LIGO in gravitational waves. So that gave me some sort of pleasure to 1 decimal point. So they need to do 11 more, and then I'll be in business. Okay. So where are we with this? What we've done, what's happened since, now that we think that this is true, we can turn the light bending around and make it a tool for astronomy. Okay? We can use the fact that light bends to try to figure out that if we put something in between us and the source of the light, then the light will bend and therefore the shape of the source will change. So this leads to what we call gravitational lensing, and effects like the Einstein ring, this thing where we see a distant galaxy doesn't essentially display itself into a ring. The famous Einstein cross, where one distant galaxy appears to have 4 images. We know they're the same because of the spectral information and so on from each of them, and the variability. Or this deep space image from NASA that shows things like arcs, rings. You see one here. It's a little bit difficult to see, but you can see many stretched galaxies. So what you can imagine doing with this is you can ask yourself, what has to be in between me and these galaxies in order for this image to look like this? And you can realize there has to be a lot of stuff here that I can't see. What we call dark matter. Something that leads to gravity, but that doesn't shine. And so actually what we're doing now is we're turning Einstein's idea of light bending around and making it a tool for astronomy. And it tells us that in the universe there is about 1/4 of the gravitating mass material that we can't see, what we call dark matter. We don't know exactly what it is, we can't see it. Okay. Now if you imagine taking this light bending to the extreme, you can ask, is it possible for space to bend so much that it traps light? So if I try to shine the flashlight out from this region, I cannot. Light is trapped, it keeps on bending around in circles. The answer is yes. That's what we call a black hole. So basically a region where you pile matter into a very, very small volume until light gets trapped. So I'm not going to talk very much about black holes, I just want to show you a couple of images about the idea. So black holes were totally confusing the scientific community until the 1960s. And so largely due to the work of John Wheeler, who was quoted earlier, and his students basically formed a new school in the United States for understanding gravity. We now understand black holes much better. But you can ask yourself here, where would this part of science be if we kept calling these black holes what we called them before the 1960s, and when John Wheeler invented the name black hole? In the West, they were called frozen stars. No, completely collapsed objects, and in Russia they were called frozen stars. Neither of which actually sound particularly exciting, and neither of which actually describes what is actually going on. Black hole sounds much more evocative, I guess, although the French didn't like it much. But there you go, we don't really pay much attention to the French. And so, it's actually quite a funny story because John Wheeler invented the name black hole, and he said that, the way he told the story at least a couple of times, is that he got fed up, saying completely collapsed objects. He said, well, once you said that 3 or 4 times during your presentation, you have to look for an alternative. People just glaze over and think, well, and so apparently one day when he was lying in his bath, the idea of black hole being the name struck him. And then he said that at some conference talk, and since then it stuck. He wasn't sure that was such a good name, but that's where we are. Of course, now we're seeing black holes all over the place. And so let me take you through why we think that is true. So the first real evidence that there are black holes in the universe came from observations with the Uhuru satellite, which opened up X-ray astronomy in the 1970s. So this is 1971. So up here we see a map of the galactic plane, the equatorial plane there, showing basically the strongest X-ray sources seen by this experiment, and a modern picture of something called Cygnus X1, which is a very compact object going around a partner. It's a dark object, so we can't see it. It has to weigh about 15 times as much as the Sun. We have no explanation for what this could be, and so we think it should be a black hole. It's very indirect, this logic. Okay? It basically says, it weighs this much, it can't be anything else. You can come up with other explanations, but actually, if you do, you have to take steps away from something being simple. So with Occam's razor kind of in mind, you land on the simplest possible explanation, and that is that this is indeed a black hole. We have many objects like this, and basically they shine in X-rays as material falls onto it from a disk going around it. So basically, these guys devour their binary partners. It's like a one-way marriage where my wife makes all the money and I spend it. Or, sorry, it's like a family where I make all the money and my kids spend it. So this is the emission of money. Anyway, and so the matter heats up, it forms, is spewed out by the black hole in a very strong X-ray jet, and this is what we see. Infamously, of course, or famously, we have Stephen Hawking's. We know black holes are true because Stephen Hawking conceded his famous bet with Kip Thorne, so therefore they have to exist. Or you draw the conclusion that Stephen should not be betting. So he has a very bad track record in bets. I think he's conceded every single bet he ever made. I, on the other hand, have never conceded any bets I made because I never made them. And they wouldn't be famous, so maybe it's just not. Okay, but since then, we've learned more, since the 1970s. We've learned that pretty much every galaxy harbors a massive black hole at its center, starting from the observations of the galaxy M87 in the mid-1990s, where gas was seen to swirl around the central part of this galaxy, so you can measure how fast it's going on one side compared to how fast it's going on the other side, and you try to weigh what's in the middle. And you find that this would be a black hole weighing something like 2 billion times as much as the Sun. So this is a behemoth of objects. To the water maser, so this is the water equivalence of lasers, a stimulated emission water from NGC 4258, if you recall the number. It's probably some sort of galactic helpline. Where the same kind of argument now from these masers suggests that there is a black hole weighing, I've written it down in fact, 40 million times as much as the Sun, so slightly lighter, but still quite big. And then the best evidence we have for these big black holes actually come from our own galaxy, fantastic work from the Keck telescope, where they track, so these are the orbits of stars near the galactic center, where we see stars over a decade, a little bit more, complete orbits. So these are obviously ellipses, some of them are extended where they would be in the distant future, and then you can basically say, okay, so what has to sit in the middle, which is something we don't see, is dark, what has to sit in the middle for this to actually happen? And you work out that there has to be an object there that weighs about 4 million times as much as the Sun. So maybe the best evidence, apart from what is going to come when Ian Jones gives his talk, in gravitational waves. The best evidence before that came from our own galactic center. So there are gigantic black holes out there. But if you ask, how close are these stars to that black hole? The answer is not very. You can squeeze in a lot of things in between these stars and that black hole, because black holes are still small, although you still have to stretch your imagination if you want to figure out, as a theorist, what it could be. And so the black holes are, again, the most conservative explanation. Okay, so I'm going to wrap up, because my time is almost up. I just want to talk a little bit about trying to weigh the universe. What happens if you look at the cosmos and you try to explain the entire universe? And that's maybe the most grandiose of scientific plans. I'm going to explain everything. So here's a modern picture of what's going on. And basically, in the early days, as we'll hear straight after me, there was a discussion as to what the cosmos was like. Einstein realized that every single solution to his mathematics was, in principle, a universe. Most of them would not be universes like the one we live in, but they would be universes. So you can ask the question, is it possible that these equations describe the universe? So Einstein decided that the answer to the equations he had was no. He didn't like it because, at that time, it was generally believed that the universe was static. It did not evolve. Stars and galaxies sat where they sat, evolved over a very long time, so there's nothing. So Einstein figured that gravity, his solutions would either expand or contract. They never just sat there. And so he put in what he called the cosmological constant, this lambda. It's a piece that is allowed mathematically, he put it in. And what this term did for him was it allowed him to have this static universe. Of course, famously, as we'll hear soon, it was discovered that the universe is expanding. Distant galaxies move away from us. That was Edwin Hubble's contribution. And so Einstein got a bit miffed. He put this term in to make sure that the universe didn't evolve, and then Hubble goes to find that actually the universe does evolve. So now he drops this term, and people say that he said it was his biggest blunder, etc. Okay. So now let's fast forward a little bit. So this is a term that instead of making gravity pull, it makes gravity push a little bit. Basically to hold back, so it doesn't, because the universe doesn't collapse on its own. So since then, the big story here is this term never really went away. Einstein dropped it, but it never really went away. People think it should be there for a theoretical reason, although most people put it over on this side with the stuff. Okay? People should think it should be there because of quantum physics. I'm not going to talk about that. But now we also think we have evidence for why it should be there, because when we start seeing evidence for not just the expansion of the universe, but the possible origin in the Big Bang explosion, starting from Penzias and Wilson and their really funky-looking ear to the universe in 1964, through to things like space missions like Colby, WMAP, and most recently Planck, which basically tried to take snapshots of the temperature of the entire sky, the temperature of the sky corresponding to what happened in the universe when the universe was about 400,000 years old, when radiation that we see decoupled from the stuff, from the matter. And so what you can see is these increasingly high resolution speckles, and basically what this tells us is something about the quantum, very small scale fluctuations in the original Big Bang explosion. So what this has done over the last, maybe the most exciting thing in this entire kind of story is that over the last 10 years or so, cosmology is becoming a quantitative science. We're not speculating about things, we're doing detailed measurements. But these measurements are a little bit problematic, and if you're an advocate of Einstein being right in every account, it becomes a little bit confusing, because when you go back and ask yourself, well, what is the stuff in the universe? How much does the universe weigh, and what do we have to do to reconcile these observations. The most recent ones from supernova explosions show us that the universe is not just expanding, this expansion is accelerating. So the universe is accelerating faster, but it's speeding up faster and faster, gradually. So to achieve that, you need to put in this cosmological constant to push. But here's the problem. What we see in the universe makes up only about 5%. All the stars, galaxies, people, really big people in other galaxies, whatever you want to put in, is 5% of everything. About 25%, a quarter, is dark matter, which we need, as I said, to explain gravitational lensing. So this we can understand. We don't know what the dark matter is, but we know it has to be there. 3/4 of the universe, or nearly 3/4, 70% say, is something else. It's the stuff that pushes. We call it, or people call it, dark energy in Star Wars kind of fashion. The Force, whatever it is. But the problem is, we have no idea what this is. No idea. So, either Einstein's theory doesn't quite work on the huge scales of cosmology, and that's why people are looking for other alternatives, whatever, or theoretical physics needs to get its act together and work this out. So this is one of the biggest challenges, I think, for fundamental physics today, is to understand why these fractions of the universe are what they are. And sadly, we have no idea. So maybe I shouldn't finish by admitting failure, defeat, so let me finish with something slightly different. Now I've talked about esoteric things like your head being a different age from your feet and so on, curved space, blah blah blah, black holes, gravitational waves. This has got nothing to do with your everyday reality, right? Nothing. Only it has everything to do with your everyday reality because of the global positioning system. So, unless, of course, you're like me, you refuse to use a sat-nav for driving or look at your phone, etc., to figure out what's going on. But the reality is that if you have one of these, or some other make, so I'm not advertising, you might be using the global positioning system regularly, and when you do, you rely on general relativity to be correct. So the GPS system is a multi-billion-dollar system with 24 satellites going around the Earth. They go around the Earth twice every day, so they move much faster than us here on the ground. And basically, that has two effects. The first one is because they move at relatively high velocity, we know from Einstein's special relativity that those clocks will appear slow compared to us on the ground. So now if you work that out, that effect means that each clock, its moving clock, will slow down by about 7 millionths of a second every day. So divide a second into a million pieces, take 7 of those and put them in a plot. It doesn't affect everyday life, right? I think. If I'm 7 millionths of a second late for something, no one really complains. Because there's always someone else that's half an hour late. Now, if you consider now that you're at high altitude, the clock at high altitude, according to general relativity, will run faster than the one on the ground. Now, that turns out to be an effect of about 45 millionths of a second. So now we have to do some very complicated mathematics. We have to add these two numbers together, -7 plus 45, or the other way around, -45 plus. So we get some number, you can work it out, there will be a test later. But the upshot of this is, if you didn't have both of Einstein's theories of relativity, and if you didn't account for them in the right fraction, the errors of the GPS measurement would accumulate by about 10 kilometers in a day. Now, if you want to do your sat-nav driving, I suggest that that might be problematic. So here's an everyday example of why we need both special and general relativity, and why you should give researchers loads of money, and why we need to have events like this and enjoy ourselves. So I'm done. So basically, we have tested general relativity in a number of different ways, many, many more than I've had a chance to talk about. Over a wide range of scales, the theory seems to work. It explains what we see in the cosmos, no doubt. But we don't know if the black holes that we think we see are the black holes of Einstein's theory or something like that. We haven't got a precise measurement there. We don't understand this dark energy of cosmology, and we have no idea still proper how we marry Einstein's gravity that explains things on larger scales with quantum physics that we know works on very small scales. That problem has been with us since the 1920s. You could argue that we're not much closer today than we were then, although of course there has been progress. We've got string theory and things like this, but these are still incomplete. So I'm over time. I'm so very sorry. I'm going to stop that.